So now we can actually do some experiments and work out what enthalpies are. So we need to use a couple of formulas here. So the first one is Q equals MC delta T's. So we're going to calculate the heat, which is Q, and what's going to affect the amount of Q. So how much substance there is going to affect it. So this is probably one of the things that people stuff up the most. It is the water that is containing the solutions. Sometimes we're adding like one volume and another volume, so don't forget the total volume. And so that is what the mass is. Now, that particular mass for chemistry, we just generally just use water. So it's these are in the data book, at least these two formulas, and the 4.18. Double check that you're using joules, Kelvin, grams consistently, not kilojoules, kilograms. You could do that one if you wanted to, though. And so that is the specific heat of water, which is quite high. So it takes a lot of energy for water to heat up and a lot of energy to cool down. The metals have like decimal places quite low, so they heat up and cool down quite quickly. I forget how many decimal places they are. And obviously the temperature change. Now you get a little bit, you can kind of cheat with this one because temperature change in degrees Celsius will be temperature change in Kelvin, but be careful for gas laws and stuff. It's often not the case. Always convert to Kelvin. But for delta C, for Q equals MC delta T, for delta T, it's always going to be the same, no matter if it's Kelvin or degrees Celsius. So we'll skip the conversions for that. And then because we're dealing with standard conditions per mole, the Q is just the energy change, the enthalpy, like the real enthalpy, the change in enthalpy, not the change in enthalpy with a little delta there, even though I keep saying enthalpy all the time. So to work out the standard enthalpy change of reaction, I think I've said that correct, we actually have to divide it by the number of moles, so get Q and divide it by N. So that's all you need to get your enthalpies, quite easy. We usually use a calorimeter, not a colorimeter, which is a spectrophotometer. That's different to a calorimeter. They sound the same. And so usually we're trying to insulate it to stop heat loss. There's a mixer there. There's the thermometer. This is pretty dodgy, actually. You should always try and use a data logger. Thermometers are imprecise and unreliable. And that's how we do it usually. You can do it in a beaker because, I'll show you there, first of all, the errors. Always, this is like a standard thing. They always ask, why doesn't it work? It's because the heat's gone somewhere else. Okay, so I don't have this one happen too often. Gas is coming off. That's a huge error. So the heat's all gone somewhere else. You haven't even tried to collect it. If you're burning something, I guess that's what this one's talking about, not putting a metal inside some acid and hydrogen gas coming off. But when you're actually burning fuels underneath it, that's the common experiment, and that's pretty terrible. The heat's all going everywhere but inside. Okay, and the thermometers are pretty dodgy too. As I said, use data loggers. Okay, analog thermometers are terrible. And so you can get away with it putting in a beaker or having, well, you can't get away with losing heat, but you need data loggers basically, because data loggers are going to show you if it's doing this, right? Or sometimes it's doing this if the calorimeter is really good and holding all the heat in. And so you need to know what's going on there. You need regular, reliable, accurate temperature measurements. And so what's going on is this is constantly losing heat to the environment. And so how do you know how much heat's getting lost to the environment here? Well, you draw a line of best fit over here, and then you can extrapolate it up to when you started the reaction. And so the maximum heat is not in the highest temperature that you got on your thermometer or even data logger. You need to extrapolate it up here and account for all the heat that was lost while it was heating up. And so that will be the true temperature change here. Okay, not this one here, because you lost all this heat while it was heating up. Okay, so you need to be able to do that and draw that sometimes in a test, sometimes for your experiments. So going through some problems here. These are not easy, okay? There's 3 of them. Okay, so what are we looking for? How much energy is released when 600 grams of magnesium was burnt? We know the delta H, and we know we have 2 moles of magnesium with 1 mole of oxygen. So always write your balanced chemical reaction. So there's no limiting reagents in there, and that's balanced. And so how many, what are we getting here? So the delta H for this reaction is 1,200 kilojoules per mole released. And so per mole of magnesium, it's only 600. How many moles of magnesium do we have? 0.0247. So we reverse this equation because we're looking for Q here. So Q equals the heat of reaction, or heat of moles of delta H, for delta H, not for the reaction, that's 1,200, but the delta H for magnesium is 600. And so you times it by that, and it's 14.8 kilojoules was how much energy was going to get released if you used this much magnesium. Problem number 2, 20 mils of this, 30 mils of this, same concentration, temperature increases by 12. What's the delta H? Actually, what's the heat released? Not the delta H. I think I do the delta H anyway. Okay, so 50 mils is the big trick. It's 20 plus 30. All right, and so we're assuming always, if I haven't said already, that 1 gram is 1 centimeter cubed. All right, so we're dealing with 50 grams. Okay, so Q is MC delta T. We got the 50, we got the 4.18, we got the 12. Increases by 12 degrees Celsius, 12 Kelvin. Okay, so that is our heat released, but we don't know the molar heat of reaction. I think that's the answer. That we're finished with that question, and now we're just doing extra stuff, okay, which you need to do anyway. Okay, so they could ask you what's the delta heat of the reaction. It's all 1:1:1, which is nice. They're all, and we only have 20 moles of this, so NaOH is the limiting reagent, so that saves time as well. And so that's how many moles of the sodium hydroxide we have. We have some excess HCl we don't care about. So delta H is Q on N, so divide that number over here by the number of moles that was used, and that will give you your delta H of molar heat of reaction for these things, but also molar heat of reaction for the actual reaction as well, because everything's 1. Okay, oh, and don't forget, just be sure that when you give your final answer that you've just double checked if it's exo or endo, so you got the sign right, because it's a bit annoying to keep track of the sign through all the different calculations, to be honest. The last question is 300 of this, 150 of that, react it together. We've got a temperature change there. The molar heat of neutralization of KOH, that is not the molar heat of the reaction. All right, it'll be half of that because there's 2 moles of that. So that's a trick. All right, so put all those numbers in. We've got 450 grams total. That's the stuff that people usually stuff up. This one doesn't really matter if it's Kelvin or degrees, so we're fine with that. So we got that. Now we need to know how many moles of KOH there is, because we're doing the molar. We have to know how many moles we used. Probably have to know limiting reaction too, because it's probably not clear. They're all different concentrations. No, they're the same concentration. One's half of the other. And this one is 300, which is double, and that one's half. So they're being nice to you there. They're equal. All right, there's no limiting reactant there. And so we know what the Q is. We know the number of moles of KOH. So the delta H of neutralization is KOH is that. Again, oh yeah, it has asked for the enthalpy of the reaction, so you need to double it because there's 2 moles of that for the whole reaction. So that's the enthalpy of the reaction. It is neutralization, so don't forget the sign. Make sure you put the negative there at the